Hi, I'm Luke Wilson, Chief Data Scientist in Dell Technologies' HPC and AI Innovation Lab, and I'm joined today by Varun Shankar, who's a graduate student at Carnegie Mellon University. We're going to be talking to you today about a project we've been working on in collaboration with MIT, Los Alamos National Labs, and a few other groups about using neural networks to predict fluid dynamics. Before I get started, I want to talk a little bit about the Dell Technologies HPC and AI Innovation Lab. The Innovation Lab is focused on three main pillars. First, we develop best practices and solutions for getting the most capability out of Dell Technologies infrastructure, including Dell EMC PowerEdge servers, accelerated with NVIDIA technology, as well as Dell EMC networking. We focus heavily on industry-focused research with our customers and partners, like the one you're going to hear about today. These research projects help us figure out exactly what the next generation of Dell Technologies solutions should look like in order to better create value for the customer. We also contribute back to the community quite heavily in the form of source code contributions to frameworks such as TensorFlow and PyTorch, creating interesting content in the form of blog posts and white papers, and doing peer-reviewed research like the content we're going to be talking about today. So deep learning produces an amazing array of outcomes, especially in the simulation and modeling space. We've seen how deep learning can help with brain analysis, with performing weather forecasting, and even with the identification of subatomic particles in large particle colliders. And the reason that this is so important is that simulation takes an extremely long amount of time. Creating a prediction about the future based on first principles is a time-consuming process, especially when the size of the domain becomes extremely large. When we talk about weather forecasting, we're talking about fluid dynamics. We're talking about the motion of the air in the atmosphere. And air is a fluid, and the simulation of this fluid, especially over a global scale, can require days, weeks, or months of grueling, expensive, power-hungry computation in order to make the slightest amount of progress. And so we see that deep learning can help to simplify this process by providing a means of approximating answers to these complex equations in a way that takes less time to produce, uses less energy, and is more efficient at getting science done. We're seeing an enormous amount of AI augmenting high-performance computing simulation and modeling processes, from the integration of deep learning to identify objects of interest within fluid flow problems for weather forecasting, to the use of AI to perform dimensionality reduction for extreme weather events so that we can create better predictions about when tornadoes will strike and where those tornadoes will be. This helps not only in improving the accuracy of simulation, but in helping to save lives by being sure that we're looking at the right pieces of the data at the right time with the right amount of fidelity. So in the HPC and AI Innovation Lab, we have several different resources that we use in conjunction with our partners and customers to push the state of the art in the convergence of HPC and AI. And one of those is the Rattler cluster, which is an HPC and AI testbed completely stocked with NVIDIA V100 GPUs. Rattler cluster is a showcase for the partnership between Dell Technologies and NVIDIA. It includes NVIDIA InfiniBand HDR100 networking. It includes multiple types of servers that include NVIDIA V100 GPUs and is currently being upgraded to NVIDIA's latest A100 GPU series. It has an enormous amount of storage capacity through a high-performance BGFS storage solution, and it runs the latest software stacks, including from NVIDIA partners Bright Computing, as well as the CUDA and NGC containers that allow you to get maximum performance out of your GPU acceleration. And with that, I want to hand it over to Varun Shankar, who's a graduate student at Carnegie Mellon University. He's going to talk to you about the actual research that was performed in creating these neural networks to approximate solutions to fluid dynamics problems.
Hi, everyone. Thanks to Luke for starting us off there. My name is Vernon Shankar. I'm a third-year PhD student in Professor Viswanathan's lab at Carnegie Mellon. We're a pretty big group, as you might be able to tell from the picture, but that means we're able to cover sort of a lot of ground in our research. And we have projects in many different research fields and areas. But we're all sort of united under this goal of developing and improving technologies that promote sustainable energy. And a big part of that for us is sustainable transportation. So looking at things like electric vehicles, and that's sort of been a major research thread for us. Within that, though, we have people working on problems at all different scales. We might be designing a new battery chemistry that's more energy dense, so that you can get more mileage out of your electric vehicle. Or we might be looking at something more bigger picture, like analyzing vehicle fleets, entire vehicle fleets, and optimizing the placement of electric vehicle chargers. So hopefully that gives you a little bit of an idea of the kinds of problems that we're interested in. Before we move on, I want to thank some of my other collaborators on this project, Gavin and Arvind from Los Alamos, Pithuk and Professor Schmidt from UMass, Chris Rackauckas from MIT, and of course, Luke. So when we think about electric vehicles, one of the first things we do is to try to understand some of the energy and power requirements for the vehicle. Because when we're talking about the battery, this energy and power consumption really tells quite a bit of the story. From there, knowing these energy requirements, we can say, given some battery chemistry, with a battery that's this large or this heavy, what is the range of our electric vehicle? How does the battery degrade over time? So what does that mean for the vehicle's lifetime? Can we create a battery management system that makes sure that during this power cycle that the battery is operating in a safe state? And we can also break down this energy consumption into its various components and see if we can gain any insight there. So we can run some vehicle simulations that simulate driving in certain conditions, say on the highway or in the city, and we can gather some statistics about where that power draw is ultimately coming from. And so, this may or may not be surprising to you, but for your typical electric sedan, driving on the highway, by far the majority of that energy consumption is coming from the aerodynamic drag. So, over half of that power consumption is coming from the aerodynamics. So obviously, these aerodynamics of vehicles are of great interest to anyone who works with cars, and certainly to us when we think about sort of quantifying these components and values of energy. So, how do we evaluate drag today? Well, as we know, wind tunnels still exist. So if you want experimental data, we can always sort of construct models of the objects we're interested in. We would place them in a wind tunnel and record the forces. But really, this is sort of naturally impractical for many problems. If you wanted to evaluate many different designs, there's a lot of overhead associated with creating your physical objects and running the experiment. So, really the majority of any aerodynamic and fluid dynamic analysis done today is done with computer simulation. And now the reason we can do this is because we have a very good idea of the physics behind fluid dynamics. We can very accurately describe the system with some equations, and it's really just a matter of actually solving the equations. And of course, the physics is very complex, and that's ultimately what makes obtaining solutions very difficult. So we use this domain knowledge. We construct numerical methods to solve these problems. Of course, we have some parameters that are unique to the specific case you're looking at. Maybe that's the geometry of the vehicle or the speed it's traveling at. And with that, we can compute a solution. And this really all falls under computational fluid dynamics. CFD is a very mature field in simulation. There's been many decades of research that have sort of gone into creating these methods. And there's a lot of choice, when we do this, in terms of the models that we use, as a lot of these models have a certain trade-off between computational cost and accuracy. So, if you want a fast solution, it's probably not going to be very accurate. If you want that high fidelity solution, it's going to take ultimately a lot of time. It's sort of up to the engineer to make these choices depending on what's appropriate for their problem. Is it okay to have a less accurate solution because you want to evaluate a lot of designs, or is it I want to have the most accurate solution for this problem, and so I'm willing to wait a few days for the simulation to run. So regardless, what we end up computing is the flow field in our domain of interest, and all of that sort of flow information. From that flow information, we can sort of calculate things like that we really care about, like drag forces. As we aim to improve these methods, one thing a lot of researchers are looking at, including us, is really inserting AI directly into the mix and sort of seeing if we can use it to improve this process. And really, this is part of the very rapidly developing field of scientific machine learning. And so this is where researchers are using these ML tools that exist and have been used in the past and applying them to scientific problems. And really, the nice thing about solving scientific problems with AI is that we have a lot of this domain knowledge. We already understand a good amount about how these systems operate. So when we think about sort of designing our AI, we definitely want to take that into account. So we can incorporate all this sort of physical behavior that we understand into our machine learning architectures. Machine learning has often been treated as a black box, and so here is a sort of field where we can remove some of that the darkness. AI, also needs a source of data, and for us with CFD, a natural thing to do is train with high fidelity simulation data, and this again goes back to the fact that we can very accurately describe the system. We can produce very accurate high fidelity results. It's just a matter of having enough compute to do so. So there's some initial cost associated with creating this training data, but our hope is that sort of AI is able to take that and fill in the gaps to produce an overall streamlined process that in our case ultimately speeds up these simulations. So I just want to give a little bit of background on CFD and what makes it tricky to do. And a lot of that comes from turbulence. So, I think everyone's familiar with turbulence in the common sense of the word. If you've been on an airplane and been jolted around, and turbulence really is characterized by these seemingly random fluctuations in the fluid. They can be large, they can be small, they can happen in any direction. And ultimately, it's this sort of unpredictability that creates the complex behavior that's very difficult to simulate. Now, despite all this randomness, there actually is some structure to these fluctuations, or we can also describe these fluctuations as eddies. And I'll show you this little sketch here. This is a plot of the energy in a turbulent flow as a function of the length scale. And the energy is directly related to the magnitude of the fluctuations or eddies. So, over here on the left, we're looking at the largest scales of the flow. So the large eddies. And you'll notice that the largest scales contain the most energy. And so, when we think about the relative importance of the scales, the large scales will be driving the majority of the overall behavior that we're looking at, say the drag. And the small scales are sort of relatively less important. So, over here on the right, we're looking at the small scales. We're looking at the smallest eddies. And again, these contain less energy. But really the tricky part is that they are interacting with the large scales. So these large eddies are producing small eddies, and sometimes even the reverse can happen. So in order to fully resolve the flow, we actually need to resolve the smallest features. And when we think about discretizing this data so we can actually perform a computer simulation, we need if we're looking at the large scales, we only need a coarse grid with fewer points. But since we need to resolve these smallest scales, we need a grid that's fine and dense enough to capture those small eddies. So what we end up with is lots of data, And because turbulence is local in space, that means that we can do parallelization it's not that difficult. And so CFD is very well suited to HPC applications. And yet, even with current HPC capabilities, we still cannot resolve the smallest features of engineering flows. And to show you that example, if we were looking at vehicle driving on the highway, the largest scales would be on the order of the length of the car. The smallest scales would be less than a millimeter large. And so when we think about the grid that would be required for that, we're talking about billions of points, and that's just not feasible with our current computational capabilities. So instead, what researchers have come up with is these turbulence models that make some approximations to ultimately reduce the complexity of these equations. And I'll just give a very brief two-line explanation about these turbulence models. Really, it just boils down to we only really care about the large scales, and so we create some approximations to model the small scales and how they're interacting with the large scales. So this reduces the complexity, but we lose some accuracy as well because we're making some approximations. But now we can use fewer points since we're only actually calculating the larger scales. And that makes things sort of a lot more tractable. And yet, even with all of this work to get to a problem that we can finally solve, this engineering flow that we can finally solve with all of these models, simulations still absolutely can take days to complete. This truck simulation took a couple of days, and this was on an HPC cluster. And so that's just sort of where we are with these models today. And so, this goes back to the question of, if we want to do something like evaluate many different designs, we're definitely still very limited by the computational cost, and even doing something like 1,000 different designs and simulating that, may not be feasible with what you sort of have access to. So this leads us to our specific research study. And here our aim was to build a complete machine learning surrogate to forecast these turbulent dynamics. And so, we wanted to develop this data-driven model that ultimately, is a lot faster than a simulation, but still sort of retains our important features. So, features that we would sort of consider important to the flow. So, we provide the model with an initial velocity field, which is the solution to these equations. And then it forecasts that velocity field evolution over a certain time window. Now, we tested this model on a canonical fluid dynamics problem, so three-dimensional homogeneous isotropic turbulence. This is a well-studied problem in fluids and physics. So really, there's a lot that's already known about the problem. And we can make a lot of physical insights into our model based on the predictions. It's a bit of a simpler, idealistic version of turbulence, but even so, here we're looking at a contained problem that's really sort of based on the physics of the problem. And so there is sort of a lot we can learn from it. And the other advantage of using this canonical problem is that because it's sort of simpler in nature, we can use direct numerical simulation data. And so this is where we're actually resolving those smallest scales of the flow, and there is no turbulence modeling. And so what we have is the highest fidelity data that you can get. There is no approximation. This is as close to the physics as possible. And so when we think about training our AI, obviously having high fidelity data and having the highest fidelity data is absolutely pretty great for creating accurate models. And of course, we analyze the performance of our model with standard turbulence metrics. So for many machine learning models, you would use things like mean squared error. Here, because turbulence is so random and chaotic, there's a lot of ways that you can sort of analyze turbulence statistically. And there are definitely some standard metrics that are used with numerical simulation already, and some analytical metrics as well. And so, what we want to do is compare our outputs, our metrics from our model to the true DNS data, and see if we can gain some insight from there. Okay, so how do we make this happen? Well, like a lot of scientific machine learning techniques, we're simply just reusing very similar machine learning tools that have been used in the past, and simply just repurposing them for more scientific problems. So there's a lot of nice mathematical properties that come from these machine learning architectures, and so they fit very well in the physics context. So if you're familiar with deep learning models, the traditional convolutional network is very popular for machine learning tasks, like image classification. And the way it works is you provide the model with an input image, and the model uses these convolutional filters that travel around your image and pick up certain features like edges or corners or circles, and then uses progressively more and more layers to pick up more and more features, and then ultimately output some vector of probability that tells you, is it a dog, is it a cat, or whatever. And these filters are trainable, and so we give the model a lot of training images with the right labels, and then based on your error, you learn the weights of these filters. And the nice thing about convolutions is that they're local in nature, and so you're only you're moving them around, and you're able to pick up small things. And from the context of how we sort of perceive images as well, it makes a lot of sense. We don't just look at one image and know everything about it. We have to scan the image around and sort of pick up all the features and put it all together, which is sort of exactly what's happening here. And really the way our model works is quite similar in the fact that we rely on these convolutional layers. Just like in image classification, we provide the model with initial velocity image. Although in our case, we're looking at three-dimensional data, so this is more of a 3D image. But the principle is really the same. We use a bunch of these convolutional layers, and again, this has been extended to 3 dimensions, but everything sort of holds mathematically there. And instead of outputting, a single vector that tells us, what kind of image we are looking at, we simply output another image with our next velocity field. And one of the reasons convolutions make so much sense for this problem is because these turbulent dynamics are local in nature, and so they only really depend on what's happening in some local area. So the convolution, reuses these same filters and it moves them around, in our domain, and so we're able to maintain that translation invariance that we see in the actual physics of the problem too. Now, we take this a step further as well. Since we want to output the velocity field over time, we include many of these convolutional blocks. In fact, we actually have an infinite number of these convolutional blocks. And what we're really doing is solving a continuous equation to get our output sequence. So for those of you who are mathematically inclined, what we're doing is modeling the time derivative of the discrete velocity field with this convolutional network. And the advantage of doing this is that, of course, now we have a continuous relationship with time. And so we can output our velocity at really any time within the prediction window. So it really adds a lot of flexibility to the model, and sort of gives you a little bit more physical insight into the actual dynamics of the problem. Now I'll briefly go over some of our results here. What you're seeing is, again, this plot of the energy in the flow as a function of the length scale. So the solid lines are showing the true DNS data, the true direct numerical simulation data, and the dashed lines are predictions at two different time points, where so the blue is the initial time and the red is the final time in our prediction window. So, I think the major thing to point out here is that, we have great agreement at the low wave numbers, so the large scales. So the model is able to express these large scale dynamics very well. And it's really only at the small scales that we start to see some discrepancies. And again, when we consider what's important, it is those large scales because they contain the most energy. We also see that the energy in the flow is pretty consistent over time. So the energy is the integral under these curves. And so, from the sense of creating physical solutions, conservation of energy is obviously great to see. And it means that, we're coming close to producing results that, make sense from the physical standpoint. And of course, we also see great improvements in performance. The DNS simulation might take 30 minutes to compute on a good workstation. But our ML model, because it relies on these convolutions, we can take advantage of the GPU acceleration. With that, we can compute a prediction in a couple seconds. So obviously that is very significant. Obviously, there's a lot more to do here in terms of looking at more complicated problems. But this has been sort of a great step to showing what we can do with ML and CFD. And finally, just looking to the future a little bit, here we've shown just one example of machine learning tools, impact on solving these scientific problems. And in the context of CFD, being able to do these rapid simulations really opens a lot of doors. One of the longer term projects that we're interested in is the inverse design of the LiDAR on autonomous electric vehicles. So there's a lot of drag obviously associated with those big sensors on the roof of these cars. And we think that we can optimize the placement to be more efficient. But naturally this requires a lot of aerodynamic simulations. And that's not necessarily feasible with our current methods today. But in a more general sense, I think that the explosion of scientific machine learning is happening everywhere. Every researcher is thinking about using AI in their research. I have no doubt that it'll soon be as ubiquitous as having any basic data analysis knowledge. And in many ways, this is sort of a natural step. Using data-driven models in simulation workflows has always been done. We've always used empirical correlations. We've always used experimental data to improve our models. And today, it's just simply a matter of being a little bit more intelligent about how you use the data, how you apply data-driven techniques, and where the data is coming from. So, with that, I'll turn it back over to Luke. Thank you.
Thank you, Varun. And you can see that there's an enormous breadth of different capabilities that can be achieved by the mixture of simulation and modeling and artificial intelligence. In this case, we've seen how simulation and modeling can create the data that's necessary to train a sophisticated deep learning model that can then be used to replace those direct simulations when it comes time to do design optimization and other types of operations. And most of this work wouldn't be possible without acceleration. Convolutional neural networks, direct numerical simulation of partial differential equations, all of these things can be highly accelerated by using GPU technology. And NVIDIA provides the best GPU technology on the market right now. And Dell Technologies builds an array of different server building blocks that use NVIDIA accelerators, from the Dell EMC DSS 8440, which can hold up to 10 V100 or A100 PCI GPUs, to the PowerEdge R740 and R7525 that provide an Intel or AMD based platform in which you can insert multiple GPUs as well as the PowerEdge C4140, which gives you 4 NVIDIA V100 GPUs with that direct NVLink fabric that allows you to tie those GPUs together to do more complex work, like the work that has been done with Carnegie Mellon on building these neural networks to predict fluid flow. If you want to learn more about this project, you can take a look at the NeurIPS paper. You can find the research paper at the link at the top, the research poster, or a YouTube recording of Varun giving the presentation at NeurIPS. You can also find out more about all of the other projects we do in the Dell Technologies HPC and AI Innovation Lab by going to delltechnologies.com/innovation lab or checking out our research work at hpc@dell.com.